also a methodology to go about parallel computing. Because you may write parallel programs but not know whether they're performing good or bad. Okay, so next.
Slides will
So the PDF है सर हाँ सब नहीं वो क्या PDF है
Okay. So purpose of MPI is parallel and distributed computing. That is where it started. 1991 was the first proposal about MPI. Inter-process communication and it's a RTT communication. Then so there is RTT in Unix also. You might have been teaching it in network courses or in operating system. But that's a very low level protocol. This is is quite high level in the OSI layer, and also it is more suited for parallel programming. Abstraction for communication. Standardized portable way for communication. So if I write a programming key, I should be able to communicate with the program Fortran. So initially it was defined for Fortran C. Now it is available in several other languages also. It's portable. There was another parallel effort which started around the same time. It was called CORBA. CORBA, CORBA, Common Object Request Broker Architecture. That was for object-oriented computing. But the focus there was not on parallelism as such or communication. The focus was on remote objects and communicating with them. You could always create several remote objects and communicate with them. Okay, so several of the primitives you will see in CORBA standard as well. But this is a parallel effort. There is third one which is called PVM, Parallel Virtual Machine. Okay, that PVM came around 89, and I have used it for comparing my proposal. My proposal is called Anonymous Remote Computing, which is further higher level than MPI PVM. Okay. So multi-language implementations are there. Next, I'll take care. You can relax. ऐसा करना है. Okay. Again, double click. We have to view full screen. कहाँ मिला था? ऐसे करना है? No, ऐसे करना है. Or this way. How we are? Okay. I think the exact if you get the. I think so. Okay, yes, slide. It's working. So I think you can. Message passing interface, point-to-point communication between processes. Collective communication. That means we can have broadcasts and other facilities require synchronization over a group of processes. Process topologies you can create using it. So, for example, topologies, people, when whole idea of parallel computing started, people also started thinking of process topologies, such as a ring architecture or a hypercube architecture or a grid. So, depending on the problem that you are solving, the problem naturally has a grid Then you make a grid of your processes and map them onto different processors. So that in grid, each process will have a top neighbor, a bottom neighbor, a left neighbor, and a right neighbor. And then you can communicate. And data can pass through these neighbors and percolate in the grid. So the grid can solve the whole thing. If data, naturally fits into a grid, then you can create a grid. So you can create a grid of these processes, or you can create a ring. The ring could be unidirectional, bidirectional, or you can create a tree, or you can create a hypercube. Okay, so there are specially made algorithms to work on these architectures. So that area was quite hot in very early 90s. Okay, so algorithms on hypercube, algorithms on grids. So if you study parallel algorithms, you will find algorithms tuned for these architectures. Now at that time, people even started making machines, hardware, which in fact fit into these architectures. So for example, hypercube, there was a company making hypercubes. There was a company called Connection Machines. So a lot of ideas, in the early 90s, were, during that time were poured in parallel computing, including these frameworks, software, and the hardwares. And now, eventually, we have GPUs, and further you will get more ideas as nano develops or quantum computing comes up. But so that was a time where parallel computing was at its, so to say, peak in terms of ideas and development from hardware and software, both the ends. So at that time, you had different ways of doing parallel computing. Supercomputers were typically exploiting pipelines, okay, very fast pipelines, and instruction level parallelism. And then there were small processors made for parallel computers, not a full-fledged Intel, but they were called something called transputer. Okay, transputer. There was a company in Europe from where the transputers came. India's Param computer was made up of those transputers. So each transputer had 4 links, and then you could connect transputers in grid. I have used that India's first parallel computer and written a program. In the end, I will describe something about those experiments. So now transputers are not there, but now then they replaced transputers by full-fledged processors. For example, you can use Intel processors. And now eventually we have cards, fast cards, graphics cards. After that came the GPUs, and now suddenly there is also a boom in applications that really require a lot of time. AI, training deep neural networks and all that. So you require a lot of time, and it might go over days. So you want to make it faster and faster. So GPUs came up as a solution, and people are using them. But if you go back to these ideas, you might get faster algorithms if you are able to exploit these architectures. And there's a mix of, people are talking about mix of MPI and GPUs. So to say, CUDA aware MPI is there, and it's about running the software on the hardware, porting them, but you have to keep the protocols the same. So MPI aims at standardized or portable protocol. So the call, once defined, should stay as it is intact, and in your language you can provide the same call. So if I send an integer from here, I should receive an integer from there in the other place. So an integer in C++ may get represented differently from an integer in Python, Java, but you have to do the transfer. So that's called interoperability. So Corva achieved that interoperability by defining standards of 5-6 different languages. So that idea is a core for portability. If you want these communications, if I write a program on C, which runs on, say, Linux workstations, it should also run on GPU without giving me any typing errors or without reinterpreting the integers as something different. So that is what good portability means. Okay, so so you have these synchronizations over a group of processes, and the idea is of having a process as a unit of execution, not a thread or instruction pipelines. But the granularity is huge. Process. So you can make these process topologies, which I was talking about. Then communication. There is something called an abstraction called communicators. So communicator, they essentially represent a group of processes. And you have process ranks in communicators, which basically are IDs of those processes. So you can communicate with other processes via the communicator groups. So there is a global communicator group, and then you can create your own communicator groups. So that is basically to partition the architectures and to write algorithms, in a more understandable way or more natural way. You have these communicators. You can divide your processes into communicator groups and also partition your tasks accordingly. So that abstraction is quite useful. And then you have also runtime profiling performance measurement interface. So when you want to do your parallel programs, you want to know how good they are doing. So you want to get statistics about them. What each process is doing, how much computation time was spent. So you require those routines and those calls. Then there are environment-related functions and error handling and all that. So this was some of the core functions. Next. So a little bit of history, how it evolved. 1991 was the first proposal, the very beginning of MPI ideas. PVM was its predecessor, 1989. When 1994, first MPI-1 standard came. There was no support for shared memory there. Then 96, after 2 years, you got MPI-2. Limited distributed shared memory was there. Then 2008, you have MPI 1.3. About 128 functions are supported in that. Message passing, static runtime. Then in 2009, you have MPI 2.2. 500 plus functions, C++, Fortran 90 bindings, dynamic process management. In 2012, you have MPI 3, explicit shared memory. In 2015, you have MPI 3.1, which is now called MPI 3. This 2.2 is now called MPI 2. And in 21, you have MPI 4, and 24, you have MPI 4.1. And now they are also started comments on MPI 5. So MPI 5 already discussion started. So if you want to do your comments on what to be included or problematic features, you can respond to that. So the latest is MPI 4.1. And next. Okay, so let us see. So OpenMPI is also there. OpenMPI has lot of many interesting functions and features. Microsoft has their MPI implementation. So depending on what architecture you are using, you can use MPI implementation. So what is the process? Process is independent execution unit of its own. You can write MIMD style processes. Multiple instruction multiple. So there are these four. You might have come across them: MIMD, SIMD, SISD, and MISD. So you can write these, these software architectures on top of parallel architectures. So single program you can load on multiple machines. Now every program will know the ID of that process or the rank of the process, and accordingly you can execute a different routine. So it is kind of different programs on different machines, and different data. So MIMD, multiple. You can write a single executable file, but based on rank you can switch. I have given those techniques in some of the programs which I have added screenshots. So Typically, each process has its own address space. Shared memory implementation of MPI also possible. Processes communicate via MPI communication primitives. A process can be sequential or internally multi-threaded. MPI does not assume anything, and MPI is meant to be thread safe. So what is the idea of thread safety? So for example, if you write a class, and is that class thread safe? In a sense, I have two threads which access the same class, different functions. Will something go wrong in that class's state? If the schedules one caller for some time, another for some time. Suppose I have a class with two functions, f and g. One thread is calling f, another is calling g. F is taking some time, g is taking some time. And from two threads I am calling these two functions. Now if that is the case, then if the class is not written for thread safety, typically when you write developer class, you never bother about thread safety, right? You think that the client is a sequential client. They will call F first or G first and complete it and then only call the other one. But you are not thinking of a situation where multiple threads are creating an object and sharing the same object and calling on the same object different functions at the same time, concurrently. And there may be an interleaving of them. So that might keep that object in an inconsistent state. Because I'm doing it partially, I change some variables. And the other function is using those change variables, but the change has not been taken in place fully. So that is the idea of thread safety. So when you develop your program, are you guaranteeing that your library are they thread safe? Are you guaranteeing thread safety? So if you have to guarantee thread safety, then internally you have to do some kind of locking and all that on the local state that you might be using. When you are doing something internally, you have to lock it and then complete the process and then only release the lock. So that another thread which might make the same function call will not mess up with your data. Okay, so if thread safety is not taken care of, then you may have inconsistency problems, subtle errors. Suddenly, suppose you use C threads. Suppose you use C threads in C++, or threads are there now in C++ specification. Has anyone used them? Let us see. So try to use MPI threads and see if you get the same result. So it's supposed to be there, supposed to be thread safe. You can cross-check it. The implementer should tell you about the guarantees of thread safety. Depending on what you are implementing, what you are taking. Yeah, is a standard. So somebody has to implement that standard and make sure all the guarantees given by the standard and all the protocols as per described in the standard, the implementation has to provide it. You can also, as a project, you can also cover the subset of MPI in your college, in your distributed computer course. Basic features like point, broadcast, scatter, gather, or some primitives. Try them out and see if you can provide a smaller subset of MPI primitives. Develop it from scratch. Okay, so it's basically a protocol, and an implementation has make sure that protocol works, and it comes to you as a library. Okay, so each process is so blocking MPI calls block only the invoking thread, not the other threads. If it is wrongly implemented, it may block all the threads. So that is not the idea. We should not block other threads to make sure that it is thread safe. Simple solution will be just to block all the threads. Then you are the only one execute. But that has different problems. That may put your computation in a deadlock. Because you are saying high priority task. This is a high priority task, and I will block everything else. So it's like interrupt, blocking the interrupt. So if you block an interrupt and wait for a resource, and you are still blocked, and that resource can be given by another thread, you are waiting for the resource. You are top priority, you are executing, you are waiting, and the resource is blocked by another thread. That thread is a low priority thread that has been blocked by you. Now suppose you are standing for a lecture, and you are waiting for say some tea in your class, but you are the person who gives tea, you have blocked them. The outside security have blocked them. Don't go inside. Lecture is and you are waiting. Now what is going to happen? It's a deadlock. So you have to release them to. Okay, so blocking a thread to make sure that nothing bad will happen is not a good solution. It might work if it has been proved that your computation won't take that much time and all that, and it won't block, it won't deadlock and all that. Very small, fast computations could be possible. There are things like in operating system, you have heard of spin locks. Have you heard of spin locks? Inside the kernel, you have to use them. Spin locks. Test and set. Anything else? Hardware synchro. Test and set. There are some more. Anybody remembers? Semaphore is higher level. Semaphore is not spin lock. Volume can be increased a bit. Yeah, sure. Okay, I think now it is better.
And we can keep it in your pocket.
Now it is better. Yeah, I can go hands free. Thank you. So semaphores are not spin locks. Spin locks are much small. They use variables, and is a busy wait. Mutexes is a abstraction with a concept. Test and set, and there are some more. Okay, find out. There are multiple variants, and see how they work. So at kernel level, at hardware level, you need them. High level, you have semaphores, and semaphores are slightly computation costly, putting the process in a queue and all that. And it is required for high level processes. So inside the kernel, you have to use something different, and these spin locks are used. So, but there is a guarantee there that your computation will end in a very finite time and it won't block other processes. Because if spin lock waits after a spin lock, if you wait for a resource which is never going to get scheduled, for which the process that clears the resource will never get scheduled, then you are in a soup. You will keep waiting, but it will not arrive because that process is blocked. Say you have scheduled for a meeting, you have called somebody, and that person is locked outside. Security is not sending, and you are waiting for the person. You can't leave from here, or you can't come in. So that kind of situation happens when when you block out threads. So the standard says we don't do that. It blocks only the invoking thread. If you are to block, you block only the invoking thread, not all other threads. Okay, so each process is labeled with a unique rank. It can be discovered by a call to MPI com rank. You can know what your rank is. So what happens is you create one program, and that program you distribute all over the network on many machines, and that is the same copy of the program running everywhere. Now that program has to know who am I, what is my task, what should I do. So that rank MPI will give that program a different rank every program. 0, 1, 2. 0 will be the kind of root process. You can use 0 for managing, sending, receiving, and all that. So a program can find out my rank, and then based on my rank, your logic can change. So you can have a single executable file with switch statement. If my rank is this, do this. And then you have to coordinate in such a way that the whole distributed computing, parallel distributed computing gets worked out correctly. Okay, I have some examples to show you how to achieve that. There is a typical architecture with every processor having its own memory, and this is network. Okay, next. So this you have tried this MPI run dot OpenAI. sorry, not OpenAI, OpenMPI and MPI-CC. Did you use the same or something else? Same thing. Okay, so MPI-CC will compile it, executable, and what will this do? MPI run.OpenAI a.out, what will it do? Execute? Where? This is my Linux machine. Only one. So by default it executes on 4 processors. And internally it has a scheduler. You don't know where it's scheduled. It might schedule on the same machine. Suppose if it doesn't find more machines, it may schedule on the same machine. Or if there are cores, it may schedule on the cores. If there is network and it's probably scheduled there. So the program need not know how the scheduler is doing it. So by default it creates 4, and I've got this out of every process. So one process said I am MPI process 2, another said I am 0, I am 3, I am 1. So how did that happen? Did you write this same program? Next. So here I have given one argument, number of processors 6. So it created 6, 0, 1, 2, 3, 4, 5. And every program knows what is its ID, what is its rank. Now based on the rank you can do the logic. So there is a lot of thinking